Okay, so quiz 12.3 has to do with vapor pressure and phase diagrams. If we move down here to question 1, we have a phase diagram given at right, and we're supposed to label the regions which represent each phase, solid, liquid, and gas. And, oh, give me a second here. Okay, you can see, let me show a little bit more here. We'll cover up my face. Okay, so here's your phase diagram. This region to the left of the red line is where the substance would be a solid. That's at high pressures and low temperatures. At the bottom here, at very low pressures and high temperatures, you'll have the region that is a gas. And then in between is the region that is a liquid. Question 2 says to estimate the normal boiling temperature. So the normal boiling temperature will be where the pressure is 1 atmosphere. So we'll go across here, 1 atmosphere of pressure, until we encounter the liquid to gas phase transition line right here, and go down and look at what that temperature is. It looks like that's 40 degrees Celsius. Now question 3, is the liquid phase or the solid phase more dense? Well, that depends on the slope of this liquid-solid phase transition line. If we start here in the liquid phase at a given temperature and pressure, and we increase the pressure, that will cause a transition from liquid to solid. This slope is up and to the right, or positively sloped. And that means that the solid is more dense than the liquid. The solid is more dense than the liquid. Okay, estimate the temperature and pressure at the triple point and at the critical point. Oh, that's creepy with my chin down there. All right, so now we can see question 4 and the diagram. The triple point will be down here where the solid, liquid, and gas phases can all coexist at equilibrium. And it looks like the pressure for the triple point is, I don't know, 0.85 atmospheres, maybe even 0.9 atmospheres, something like that. Although I'm looking at my answer key I wrote up earlier, and I had put that at 0.75, so those are the numbers that we'll go with here. But probably that pressure should be a little bit higher than 0.75. And then the temperature is something like maybe 5 degrees Celsius, about a quarter of the way between 0 and 20. And then here's the critical point all the way up here. And it looks like this pressure is about 2.65 atmospheres. And the temperature is just over 100, so maybe 102 degrees Celsius. I better write these numbers up here, just so that we can remember. So the boiling point, the normal boiling point is going to be at 40 degrees Celsius. Then we'll say the triple point pressure is equal to 0.75 atmospheres, and the triple point temperature is 5 degrees Celsius, and the critical pressure is going to be 2.65 atmospheres, and the critical point temperature is going to be 102 degrees Celsius. Those are kind of the important data points. And now question 5 says to use your estimates to calculate the enthalpy of vaporization. Hold on a sec, let's pull that back down here. All right, so we're going to use the Clausius-Clapeyron equation, which says that the natural log P2 over P1 is equal to delta H of vaporization over R times 1 over T1 minus 1 over T2. That's the two-point form of the Clausius-Clapeyron equation. That's what we want here. So if we're going to estimate delta H of vaporization based on these two data points, then we'll say the natural log of our critical point pressure, 2.65 atmospheres, over our triple point pressure, 0.75 atmospheres, is going to equal delta H of vaporization over R. And here we need to be careful. The value we want for R is 8.314 joules per mole Kelvin. And 1 over T1, 5 degrees Celsius, we'll need to express this in Kelvin. So that's 278 Kelvin minus 1 over T2, 102 degrees Celsius will be 375 Kelvin. Okay, so here's our unknown. We can take the natural log of 2.65 over 0.75, multiply 8.314 over, and then divide this quantity over. And in the end, what you get is delta H of vaporization is equal to 11,300 joules per mole. And we'll usually express that in kilojoules per mole. So that would be 11.3 kilojoules per mole. So that is the answer to question number 5. Now question 6 says to use the boiling point now, the normal boiling point, and our calculation for delta H of vaporization to predict what the vapor pressure would be at 120 degrees Celsius if there were no critical point. So what would be the pressure at 120 degrees Celsius? Well, this time we know the enthalpy of vaporization. We're looking for P2. We'll have the natural log of P2 over the pressure at the normal boiling point is going to be 1.00 atmospheres. That's kind of the definition of the normal boiling point, is where the vapor pressure is 1 atmosphere. That's going to equal 11,300 joules per mole. We'll want to use joules per mole to make sure that our units match with R, which is going to be 8.314 joules per mole Kelvin, times 1 over T1 is our boiling point temperature, 40 degrees Celsius is 313 Kelvin, minus 1 over T2 is the 120 degrees given in the question. That's 393 Kelvin. So if we solve everything on the right side here, we get the natural log of P2 over 1 atmosphere is equal to 0.8839. And this will be unitless. All those units cancel out. In order to undo the natural log, we'll raise e to the power of both sides. That just gets rid of the natural log, and on the left side, so we get P2 over 1 atmosphere is equal to 2.42. That's e raised to the power of 0.8. And then we'll just bring the 1 atmosphere over here to get P2, because this is a unitless quantity again. and we have P2 is 2.42 atmospheres, and that is the solution. Now, if you go back up to the phase diagram, that number won't make a lot of sense. And part of the reason for that is perhaps our bad estimate of the triple point pressure. If you used a better number and for the triple point pressure, you would get a different enthalpy of vaporization, and that might change things. But I think really the problem is that the normal boiling point, the triple point, and the critical point ought to have a rigorous relationship to each other based on the Clausius-Clapeyron equation. And I just kind of drew this chart by hand. And so there's really no mathematical rigor behind the shape of this curve. And basically it's not quite shaped right. So if this unknown substance phase diagram had been based on real data from a real substance, we would have gotten better results. But I don't think it's that big of a deal. We can still run the numbers and we can get an estimate for the vapor pressure at 120 degrees Celsius. Oh shoot, it's still going. I will stop recording now.